Bueno, a continuación, entonces, presentamos al profesor doctor Hans Mossmüller, del Desert Research Institute de Estados Unidos. El doctor Mossmüller es doctor en física de la Universidad Estatal de Colorado. Actualmente es profesor senior e investigador de la División de Ciencias Atmosféricas y director del Wildland Fire Science Centers del Desert Research Institute, parte del Sistema de Educación Superior de Nevada en Estados Unidos. Sus aportes a los proyectos que nos convocan se relacionaron con la investigación experimental y teórica en espectroscopía óptica, así como sus aplicaciones en la física atmosférica, de aerosoles y del clima. El doctor Mossmüller ha desarrollado aplicaciones en tiempo real de métodos de medición in situ de aerosoles, incluyendo black carbon, absorción de luz, dispersión, extinción, parámetros de asimetría, LiDAR y nuevas técnicas ópticas de teledetección. Además, tiene experiencia en planificación, trabajo de campo y análisis de datos de importantes estudios de calidad del aire. Hoy el doctor Mossmüller expondrá su investigación titulada Development of Novel Instrumentation for Investigating Aerosol Snow Optical Interaction.
Okay, thank you for the introduction. Let me see if I can get my screen sharing here to work. Can you see that? Does it look good?
Yes, we are seeing
Okay.
you.
Well, first, thanks for the invitation to present here. And it's a special pleasure to follow up on Martin's excellent talk, which has given us some idea of black carbon and brown carbon. And I'm going to show some examples here, what that does after deposited on snow. So here we're looking at novel instrumentation we can use to study snow albedo, snow energy balance, and a few related things. And this is work I started together with my former graduate student, Nicholas Barris, who is now at the University of Vienna, working mostly on large airplane campaigns to look at aerosols. And Nick has agreed to continue to help us with that. Then my Finnish friends from the Finnish Meteorological Institute, Jonas Svensson, Aki Vokula, have joined the effort. And I've known Aki has been a good colleague and friend for more than 20 years. He was a postdoc. He was here at the Reno aerosol experiment. And last not least, there's Machin and Francisco. And we hope to use some of these techniques within the FUNDEF project. And here's a picture of Jonas this spring in April. We were up at our field site and depositing aerosols. You see the circles here, and you see ASD spectrometer measuring albedo spectra over the whole solar wavelength range. And one thing you immediately see if you want to measure albedo spectra, you better find a nice flat surface, and which is not shadowed by trees or bushes. And so that has been always a challenge. And you want to go out on a beautiful, sunny, cloudless day, so the sky impact on your measurement is minimal. So let me back up for a moment. I'm at a place called Desert Research Institute, which is a soft money environmental research organization. It's part of the Nevada system of higher education, or the university system. And we have two locations. About 2/3 of the people are in Reno, Nevada, and maybe 1/3 in Las Vegas. And if you look at the map, Reno is very close to beautiful Lake Tahoe, and then a also beautiful desert lake here, Pyramid Lake. And Las Vegas is on the southern tip of the state, much more deserty environment. While here we are just in Reno, we're just at the edge of the mountains. And in Reno, we get 8 inches of precipitation per year, and you go up in the mountains and you get 80. So it's a really big gradient. At DI, we have 3 divisions, and I'm in atmospheric sciences, but I also work a lot with colleagues in earth and ecosystems and hydrological sciences. In particular, I run the optics and acoustics lab here, and we've been developing and using sensors for aerosol optical properties. And lately, we've been focusing on combustion aerosol, what Martin presented on, and mineral dust. Over the years, we had 6 NSF major research instrumentation grants for instrument development, acquisition, and a lot of other grants from NASA, NSF, and the whole alphabet soup of funding agencies. What happened in 2022, we got a very large NSF grant entitled Harnessing the Data Revolution for Fire Science. And we're going to study fire ecology, fire hydrology, fire processes, fire emissions, and on with a lot of robotics and computer science tricks in the sagebrush environment, which dominates the Intermountain West in the US. And I initiated that, and I'm the DI co-PI and the overall science lead. And that's a $20 million project over 5 years. In addition, we hope to get some money for snow research again, which we haven't had for a while. And that comes from a direct appropriation from the US Army Corps of Engineers. And we're going to be working with UC Santa Barbara and Boise State University on that. Now, instrument development and testing for snow work. I'm going to talk about 4 different things. An apparatus for dry deposition of aerosols on snow. And that's pretty much a rather finished project. But then parts of the apparatus mysteriously disappeared. As you will see, it's essentially repurposed metal trash cans. And so Jonas Svensson joined me earlier last year, about a year ago, and this year, and we rebuilt the apparatus. And we will use it this winter in the Sierra Nevada, hopefully go in spring to northern Finland for a field experiment in Lapland, and I'll hope the Andes and other places. Then we are working on a penetrating optical snow probe, and we build a prototype, which is not quite working that well yet, with Nick Barris, and Jonas Svensson will be here in next week for most of November, and we're going to be working on that. And the snow albedometer with artificial illumination is so far largely a concept, but Jonas and I will try to build a prototype in November and start testing it. Then testing is often a problem with snow. You can't do it in summer, and even in winter you need to drive into the mountains. So maybe somebody can mute themselves. And so we're going to do initial lab. So we're going to test a snow simulant, which we can use in a nice, warm, cozy lab. And initial testing will be this November too. The site where you already showed the picture, I already showed you the picture, is down here. And I'm just dragging a trash can up there together with one of my dogs. And if you look here, here's Reno. And this is in the mountains, about a half-hour drive from Reno, at about 3,000 meters elevation. And it's a very nice flat area. Not many people come there because the skiers prefer something steeper. Now, here's an early version of the aerosol deposition apparatus, and we nicknamed it the Martian Lander because it was actually a commercially made dog kennel we wrapped with aluminum foil. So it looked like some of the NASA spacecraft. And we used it first near Mammoth Mountain at the Joint Army Corps of Engineers and UC Santa Barbara station. And we tried to make deposition. Here's an example of a hematite deposition that was done in spring. And a week later, we came back. If you look at the picture on the right bottom, the snow had totally melted under the hematite, while the other snow was still there. And before we deposited, actually in fall, we placed water samplers with funnels there so we could analyze the water. But there we learned a little bit how difficult it was to work with such a big implement and to place it and transport it. So our development went into a different direction for a more compact instrument. And also Mammoth had a lot of logistics because very difficult to go for a day there. It's more than a 3-hour drive than just to the base of the mountains, and you need to get up. So we focused our development on the field site I just showed you near Reno, Nevada. And here is the new apparatus. It has 2 components. It has an aerosol deposition component, which is a large trash can, galvanized. We like to work with metal so we don't get electrostatic effects. And this trash can is essentially without a lid, placed inverted on the snow, generally penetrates maybe a centimeter or two into the snow, and we duct aerosol in there. And aerosols can either, and this is known as maximi, and here's minimi, a smaller trash can in which we actually generate combustion aerosols by burning things. Often we burn, if you want brown carbon, we typically burn peat or incense. Incense is a nice surrogate for brown carbon, and peat, especially if you use high altitude peat from Alaska or from Greenland or Siberia, then we get a very good surrogate for brown carbon, which may be deposited at high latitudes onto snow. And this is pushed by a pump, which pumps air into here from minimi into maximi and efficiently deposited on snow. If we go after mineral dust, we replace minimi with just a flask in which we place mineral dust, typically sieved down to 35 micrometers, and then use a bicycle floor pump to give it a push or two of air, and which pushes it over into the deposition chamber maximi. And this apparatus has been described by Nick in a AMT publication, and then the application for brown carbon has been described in the ACP publication. Nick just did a wonderful job on that. Here is the apparatus in the field. Minimi generating brown carbon. We're just burning things in there. And you see on the left top a typical burn vessel, which is a cook pot, essentially. And we lined it with some insulation, so it simulates a semi-infinite surface. We place peat in there, light it on fire, then place the hood minimi on there, get the pump going, and the aerosol cools, and this copper coil is pushed over into maximi, which sits on the snow. This is a typical location, and the aerosol is pushed onto and maybe an inch deep into the snow. Here's an example. Oh, and then we take hyperspectral reflectance or albedo spectra on the deposited surface. Here's an example for the deposition of hematite, Fe2O3, which is possibly the dominant light-absorbing mineral dust in the atmosphere. Oops, sorry, I switched here. And you see the deposition. In real life, it looks a little bit more red than what you see here. And if you look at the absorption spectra, there's a very clear and strong absorption below maybe 550 nanometers, and not much absorption in the infrared, if you compare it with the natural snow reflectance. Now, here's another example. We deposited black carbon, and there you see that there's a general strong absorption over the visible. And in the infrared, it's not that important because the reflectance goes down anyway due to water absorption in the snow. So black carbon lowers the albedo broadband in the visible spectrum. Brown carbon now, you actually by eye, you don't see much of an effect. In nature, it looks a little bit yellowish. And we see a very strong absorption in the near UV and shortwave visible wavelengths. And then by the time we get to 600 nanometers or so, 550, it doesn't have any effect. So as Martin pointed out, it's maybe not that important for the total absorption, but especially for UV photochemistry in snow and the atmosphere, brown carbon has a very big influence. Now, the next thing we have been developing with Nick, and which is not as complete, we had one field test with it, is what we call the penetrating optical snow probe. It's essentially an aluminum pole you see on the left, which has a fiber optics in it and a sapphire window at the top. So we push it into the snow, and at a particular depth in the snow, the light is coupled into the fiber optics, and on the top of the pole sits a small ocean optics spectrometer going from about 350 nanometers to 1 micrometer. So we can measure the actinic flux within the snow. And when we get to a light absorbing layer, here depicted in this, then the actinic flux will quickly drop off when we get below this layer, because the incoming solar radiation, which is diffusing down in the snow, is suddenly absorbed. So this is a way to profile light absorbing aerosols in the snow spectrally, and also to distinguish if that's mineral dust or brown carbon or black carbon or something else. So additional applications, we can point the dam tip up, and it's essentially a cosine detector. So we can measure the downwelling solar radiation, the irradiance from all angles. If we additionally point it down above the snow, we can get an estimation of the surface snow albedo. And then what I just described, we can look at the snowpack extinction, optical extinction versus depth. And what this apparatus still needs is a better operational thing. Right now, the spectrometer sits on top, and the stuff to push buttons when you hold it over your head. And in addition, we don't have an automated measurement of how far the tip has penetrated in the snow. So we're going to add a small distance slider to the top box, so we know how far the top box is above the snow surface. And by inference, we can figure out how far the tip has penetrated into the snow. So that's on our work program for November. Then snow albedo measurements generally depend on solar illumination. We need the sun out, we need a clear sky, we need a flat surface, and that's sometimes difficult, especially if you want to study high time resolution events like snow metamorphisms in spring, where we go through a melt-freeze cycle. I would really like to do hourly measurements, but if we can measure only close to a solar noon, then that's not really feasible. And in addition, we can study aerosol deposition and the effects with high time resolution. We can also measure in the forest, on steep slopes, and places where the conventional snow albedo and spectral snow albedo measurements are not really feasible. So here we have so far a concept, but I've just ordered parts for it. And we're going to work in November on it. It's essentially using an integrating sphere or hemisphere, where we have a light source fiber coupled in, and then the signal goes into the spectrometer. And then we have an opening in the integrating sphere which faces the snow. And that's a common thing you can use to measure surface albedos, and you can calibrate it with NIST traceable albedo standards, which we have in our lab by just sitting on the albedo standard and going from maybe 1% reflectance up to 95% reflectance in different steps, and then do linear regression between the optical signals you see and the reflectance of the albedo standard. So why can't we easily measure snow albedo with that when we set it directly on the snow? The problem is that solar light can penetrate in the snow quite far, and it can sneak off to the side. So it gets lost and not reflected within this aperture while it's not being absorbed. So for solar measurements, that's no problem because we illuminate an infinite surface. Here it is a problem, so we need to figure out how we can correct for it. One way is to add an internally reflecting cylinder out of aluminum or Teflon here, so light can't escape. The other option is to check out this effect as a function of aperture size, and it will get smaller with larger aperture size, so possibly we can correct for that by doing some kind of a regression. Then this albedometer could also be used in a snow pit to profile the historical albedo of aerosol depositions as a function of depths in the snow pit. So you put it on the side surface of the snow pit and do measurements at different depths. So this will be very interesting to see where the light absorbing material actually sits in conjunction with the faster measurements with the penetrating snow probe, and give us also an idea where the snow is heated, because the snow heating does not just depend on snow albedo, but it also depends at what depths in the snowpack it occurs and will differently affect the snow melt. Then artificial snow simulants. I was gone till last night working in Maryland, but I just ordered this styrofoam beads from an art store, and I was finally able to find some very small ones, 0.5 to 1 millimeter in diameter. And they're waiting for me at the Institute right now. And so we're going to fill a cook pot or some volume with them. And then we can test, for example, the penetrating snow probe or the snow albedo instrument on a snow surrogate, and do some initial tests and debugging of the instruments in the laboratory, which will be very convenient, especially right now as we don't have any natural snow up in the mountains yet. And summary and conclusion, we hope that this novel instrumentation will become available in 2023, and then we're going to do some transformative studies of snow energy balance and the impact of light-absorbing particle deposition on and in the snowpack. And we also hope we're going to have some fun and do some skiing on the side, and one of my dogs or two of them can come along again. So thank you for your attention. And if you look at this last picture, this is Mount Shasta, the highest mountain in Northern California, more than 14,000 feet, above 4,000 meters. And you can do a wonderful ski run, in this case in July still, in northern summer, all the way down, dropping more than 2,000 meters. And the bottom here, you see the snowpack. You see some graying, which is from mineral dust deposition, likely from this nearby volcanic debris fields. And in the front, I hope you can see this reddish tint. That's from snow algae, which have started to bloom on the snowpack. So thanks a lot for your attention.
Thank you, Hans, for this very interesting and exciting work for the new instrument that you development for research snow and the labs in the futures. Yeah, I think this is a very creative experience to create new instrument, and I love that. That is very, very interesting. Thank you for your presentation in this case. One question about the experiment that we make together in the past in Portillo about the cylinder. You using this warm combustion system that produce aerosols, produce this black carbon or a brown carbon, aerosols. But what happened with the temperature? Is possible that you modify the granulometry from the grain from the snow, like we have the experience in Portillo? What happened with what is the solution for this problem that we experiment in Portillo, also with the gas from the vehicle that we're using in this time? Do you remember that? No?
Yes, that's a very important question. In Portillo, we directly ducted the diesel exhaust onto the snow surface, and we quickly learned that the diesel exhaust is warm, and it induces some melting followed by some freezing on the snow surface. So if I go back here and show up, here's a picture. Here's warm smoke from peat combustion coming out of here, and then we have these lengths of copper tube we don't really need, but we wrapped it into a spiral. And so here in this 1/4-inch diameter tube, the exhaust cools off to near ambient temperature. So, and a lot of it condenses, of course, on the top copper surface too, but as a result, we deposit fairly cold smoke into this volume. However, there's still a problem because placing the trash can in there stops any light winds. We're trying to go out when there's no wind, but there's always a light breeze going up in the mountains. So the temperature of the snow surface changes even if we just place this large trash can Maximi on there, because the radiation is different, the wind doesn't have an effect. And so what we have been doing to at least control for that, you can see the influence of the grain size and the reflectance spectra. And so with that, you can get an idea of how much the grain size has changed. In our experiments, we were able to keep this influence fairly low. And Nick has detailed, discussed that in detail in his publications.
Yes.
But yes, so we are trying for dust deposition. We really place it only for 5 minutes on there and take it off as fast as we can. And for combustion aerosols, we generally run this for half an hour, which has a larger influence on the snow surface properties. But excellent question, Francesco.
Mm-hmm. Yes, thank you. Yeah. I imagine that this so expiral was the solution for cooling the system, the cooling the gas that coming for the combustion process. But anyway, you lost some particles in the condensing. But anyway, we can characterize the final position of the emission source. What is the type of aerosol? What is the measurement of black carbon, and also the size of the particle that you produce finally in your spray? No? Yes.
Yeah, and it's a very manageable apparatus. 1 or 2 people, we carried it for maybe a mile distance to a field site on skis or snowshoes. So it's not something you have to be at the roadside. The Finnish folks had a very different approach, placing a 5-meter diameter enclosure with a crane on a snow surface in an unused airfield. And so they got very interested in this more mobile system.
Yeah, maybe in your case, another system that is more simple for mineral dust is without this problem. Huh? Is it efficient also?
Yeah, I mean, mineral dust deposition, there's no heating involved.
Yes.
Can deposit the dust very quickly within 5 minutes. So placing the deposition volume onto the snow doesn't affect the snow surface very much.
When is it homogeneous, the distribution of the particle also?
We can look at the pictures.
Yes.
And generally it's fairly homogeneous. However, here, for example, we see a lighter deposition on this edge. And we see that mostly when the wind is blowing. When the wind is blowing, wind penetrates into the snowpack and can penetrate a little bit into the deposition volume. And so then you get a less homogeneous deposition. But in generally, we have been quite successful. Now for albedo measurements, of course, as we know, and Machin and you and I have been doing calculations on that, the finite diameter is always a problem. And so we hope that the snow albedometer will allow us to make progress on that too, because there we just need a 1 or 2 inch diameter to probe things. And within a 1 or 2 inch diameter, the snow surface deposition will be very homogeneous.
And you measured the albedo after the deposition without the cylinder, the metallic cylinder, no?
Yes. So here is a picture of, let me see here. Jonas has a snow albedo measurement. So we have a probe with a cosine detector here, so which we place as low as we can above the deposition circle, while still avoiding shadows from the apparatus to go on there. And then here we have an ASD field spec 3, which measures the whole solar spectrum. And that allows us to get the albedo. And you clearly see how the diameter of the deposition volume is reflected here in the deposited area.
Mhm.
So it's not perfect, but we're getting somewhere.
Great. Thank you, Hans. Thank you.